Hi, welcome to another TI Tuesday. This is the breadboard and this is August 22nd, 2016. In last week's episode we looked at a current shunt sensor that used an external current shunt resistor and had a differential voltage capability up to 76 volts from zero, and the supply can also work up to that range for the chip itself. What I have this week is the INA301 current sense resistor. It is different from the one we looked at last week in that it can do high side or low side current sensing. It also has a comparator built in to allow you to set an alarm output based on a threshold being exceeded, and that could be fed from either a set resistor or a D to A converter feeding into the input. There are two GPIO pins on the device, one of which is an input to either reset the alert output, or to, if you hold it low permanently, it will allow the alert output to simply follow the threshold. So if it's above threshold it will turn on, if it's below threshold it'll turn off. If the reset line is held high, then the alert output will latch, so even if you had a transient for a few microseconds you would be able to detect that, and under program control or a button or something like that you could then reset it and wait for the next event to occur. This is a purely analog chip. It basically has the op amp with the differential inputs with the high common mode voltage up to 36 volts, and then it has a comparator op amp built in the same device, which has some hysteresis built in so that you don't get the thing oscillating when it's very close to the threshold. And also it has those two logic controls one logic control, one logic output, to allow you to indicate whether you've exceeded a threshold. It does have enough current capacity to drive simply an LED too, if that's all you wanted to do with it, and that's what we're going to have as part of our demo as we go through and have a look at this. So I have them set up on the breadboard here. I have two of them set up. One is a times 50 gain device, the other one is a times 100 gain device. I have two current sense resistors. Last week we were just simulating the current sense differential voltage going into the chip. This week I've set up with a proper current sense resistor, and they're both 50 milliohms, one feeding each chip, and they're in series. So you can actually do that quite happily, and when we get to the alerting you'll see that I've got one which is working effectively as a partial alarm, maybe a warning that we're getting the current a bit high, and then the other one when we're getting more than 50% of the second comparator. So I set them up to be 2.5 volts on the input to the threshold, so that if whatever the gain is, whatever the current shunt resistor is, when the output of that first op amp exceeds the 2.5 volts it should trip the alert. Anyway, that's partway through. I'm jumping ahead of myself here. Let's go and have a look at the datasheet, and then we will go to the breadboard and we will have a little play with the device, first of all without the alerting circuitry being connected up, and then we will go back and add the alerting and have a little play with that as well. So this is the datasheet for the INA301. There are three basic derivatives, as you can see here. There is the A1, the A2, and the A3. Each one having different gains of 20, 50, or 100. The two that I have set up on the breadboard are a 50 and a 100. They have a wide common mode input voltage range of 0 to 36 volts, and they have dual outputs, one being the regular amplifier and one being the comparator output, which is more of a logic level output, but it's an open drain, so you can put a pull-up resistor and limit how much current can flow down there, but you could pull it up to various voltages within the range of the chip if you like. You can program the alert threshold, and we'll look at the block diagram in a moment, using a single resistor. You can also do this using a D to A converter, as I've already mentioned. It has a fast alert response time of only 1 microsecond, which is probably quick enough for most applications. It has an open drain output with a latching mode too, so if you wanted to trip on a spurious overcurrent sense or something like that, then you could do so, or you can actually set it so that it follows it. When the current's over, the output goes low. If the current returns back to a normal value, then the output would return back to normal as well. I'm not going to read every single line of what's in here. You could read it for yourself, and I will provide the link to this datasheet. The chip works on 2.7 to 5.5 volts, so I was slightly overestimated than that before. Comes in an 8-pin VSSOP package. This is the block diagram for the chip, and you can see here we have an external current sense resistor where it can take a common mode voltage of 0 to 36 volts and a supply voltage going in separately of 2.7 to 5. Unlike the chip that we looked at last week, the load voltage and the supply voltage cannot be tied together unless, of course, they're going to run at no more than 5.5 volts. In this application, though, that I've set up on the bench, I'm supplying it separately with a 5-volt bench power supply and driving it with a current source that can supply up to 5 or 6 amps. Now, I've got two current sense resistors of two different types from Vishay. One is a large FHR4 variety, and the other one is a small TO220 package type of sense resistor. And we'll have a look at those when we get to the breadboard. You can see here the simplified diagram. You've got your differential inputs to the amplifier, which is providing the times 20 times 50 or times 100 gain, and then the output, which can go to an ADC or even just simply a display if you wanted to. The alert output from the comparator that has hysteresis. Now, the limit input is set either by the resistor or by a DAC, as we already mentioned, and then you have a reset line going in from a GPIO pin. Standard 8-pin type of package, but as I said, it's a VSSOP, so it's small. In order to use it on a breadboard, I've had to put it onto a header. So you can see here, you don't have to have too many pins connected up to make it work. 5-volt supply, a ground, the in, plus, and minus, and really, if you want to do anything, if that's all you need to do, and you don't not worrying about limits, then those are the only pins you need to set up. Has an extended temperature range of -40 to +125, so it's suitable for industrial applications from a temperature perspective. Hysteresis, which is for the comparator here, 20 millivolts, 50 millivolts, and 100 depending on the gain. So what that means is that once you trip the alert, then the input to the comparator would have to drop 20 millivolts before it would clear it again, or 50 or 100 depending on what chip you're using. This in itself prevents a lot of oscillation issues and things like that. Now, with the datasheet, you can also have a look at all of the different test parameters and charts that they've got drawn up here for helping you decide whether this component will be suitable in your application. And then we go on to a detailed overview with some kind of a slightly better functional diagram. What it's showing here that's really different from the previous one is that the RSet pin for setting the comparator threshold, they're drawing this more as an op-amp now comparator rather than just a single input one. But there's a current source feeding on the RSet, and you will see in the datasheet, if you look, or we'll see it later on, that it has an 80 microamp current flowing through here. So if you're running this output, say from 0 to 5 volts to represent 0 to 5 amps, and you wanted to trip at 4 amps, you would need to arrange for this to have 80 microamps at 4 volts, because that's what would be coming out here to represent the 4 amps, which would mean you'd need, I think, a 50 kilo ohm resistor in the RSet position. Now, of course, if you're driving this from a D to A converter, then you don't need the RSet, and you'd feed it directly from the D to A. Talks more about adding some filtering to your current sensing. Now, if you've got a noisy supply, you don't really want to have that being reflected through your current sensing. So you can use some RC kind of filters to prevent that getting to the differential amplifier of the current sense chip. So even though the current across the current shunt resistor is maybe fluctuating and it's got some high frequency noise, you can pretty much eliminate that by a simple RC kind of filter as it's shown here. For more information, read the datasheet. Here is an example of using it in a bidirectional alerting kind of configuration where they're not so interested in the outputs of the main differential amplifiers, but they're interested in limiting the current in both directions. So what they do is they've got one chip configured with the plus to the top side of this current sense resistor, and the other one, the plus is configured to the bottom side, so that the top chip would work going from 0 to full scale output in one direction. When the current reverses, it would go to 0, but it would just stay there. And this one, the bottom chip, would then carry on with the negative side of the swing, and its output would go high as the current started flowing in the opposite direction further and further. Now, these are two separate outputs. You could monitor them through a pair of analog to digital converters if you wanted to. The chip that we had a look at last week is an example where you can have a reference input to the chip and actually bias the output halfway up its range, so that you can actually have a positive and negative swing all in one chip. But that one doesn't have an alerting capability. You would have to do that in software or add your own comparator to that chip. A little bit more on design procedures, laying out your chip for ideal ideal PCB traces and things, recommended layouts. So you can see here you've got big tracks for the current going into the resistor. Now you can see that they're clearly not tapping off the resistor within these power supply tracks. They're actually bringing it on the other side of the pad of the resistor. They're effectively emulating a Kelvin connection. Now you could also use a Kelvin resistor if you want, and what I'm using on my breadboard is exactly that, so that I don't overheat the contacts on the breadboard. My actual current path does not even go into my breadboard, only the voltage sensing, and we'll have a look at that in a minute. And that's pretty much it in the datasheet. So I have two of these chips hooked up simultaneously on the breadboard. As I said, they can tolerate a 36 volt different common mode voltage compared to the 5 volt supply. So they're both running on the same 5 volt supply, but they have their current sense resistors put in series. And I'll put a diagram up right here so that you can see that. Anyway, that's enough of the data sheet. Let's go to the breadboard and have a little bit of a play with it, and then that'll be a wrap. So this is actually quite a nice chip, but we'll leave you to be the judge whether it's suitable for your own application. So the first setup I've got is the minimal one without having any alerting on. So we'll give that a quick check, and then we will add a little bit of alerting capability using a couple of potentiometers from the 5 volt supply, and we'll put some LEDs on the output of the comparator, the alert output. So let's go. So here is my setup. I have 3 multimeters. This first one is actually in series with the current. So you can see here I've currently got 500 milliamps, well 0.4999 amps passing through my shunt resistors that are down here. I have on the output of the first current sense chip here, the INA301, this is the A2, which has got a gain of 50. And then on the second chip, the INA301A3, I have a gain of 100, and that is reflected on this last meter, as you can see, is showing 2.49. Now it's a 50 milliohm shunt in both cases. These two components here, let me just turn this around and see if I can show you a little better. These are a pair of 4-terminal Vichy current shunt resistors. They're both 50 milliohms. As I said, this one is the FHR4, which is capable of taking quite a bit of power. It's got a heatsink built into it, so it can take about 10 watts of power dissipation. The one down here is a slightly different model. It is the, trying to see what it is. This is an FHR4 T220. This one is an FHR4 3825H. So very different packaging. They're both based on Vichy's bulk metal film technology. And the thing about these particular current sense resistors is they are ultra stable. They do not drift hardly at all over time, and so will provide a long-term stability for any system or circuit that you put them into. Vichy were kind enough a couple of years ago to provide a bunch for me to use for my videos, So I know that these things are going to be pretty accurate. Now, the big one happens to be 0.1% accuracy. The smaller one is 1% chip resistor. So either way, they're good enough for what we're doing here. We're not trying to demonstrate absolute precision right now, just the operation of these INA301 current sensing chips. So what I've done, if I just zoom in on the chips themselves for a second, as you can see, I think, all I've got here is plus 5 volts on pin 1, ground on pin 4. I've got the output is on pin 2, and the current sensing inputs are on pins 8 for positive and 7 for negative on both chips, and each one goes to a separate current sense resistor. But the current sense resistors are in series, so therefore they're sharing the exact same current that's passing through them. So both meters should read, within the tolerances of the resistors, of course, the same relative value. Now remember, one of them is times 50 and one of them is times 100 on a 50 milliohm resistor. So right now with 500 milliamps going through, if I just do the math on that for a second, what I will have is 25 millivolts going into both of these sensing chips. Now because one has a gain of 100, I'll get 2.5 volts coming out of it, which is this top one. The bottom one has a gain of 50, so 50 millivolts times 5, 25 millivolts times 5 is going to give us 125. And what you can see right up here, let me try and get these things to come a bit brighter again, is I've got 1.251 on the times 50, and I've got the 2.494. So they're both within their, within a couple of percent of the settings. Now, my current is 0.4999. So I'm just a fraction low, but you can see this one is within it's 0.1%, which is pretty good. And that one is connected to the 0.1% resistor. The other one is connected with a 1% resistor. Now I haven't measured their exact values yet, but 2.4 volts, 2.49, and it should be 2.5. So I'm only basically 5 millivolts out on 2.5 volts. So that's what, 2%? And the chip itself is specified as gain error of 0.1 to 0.2%. The resistor could be 1% out. So that's not too bad at all, considering it's on a breadboard and everything else. Now, if I change the current, so let's just crank the current up to 1 amp. So I'm going to make it exactly 1 amp, which means 1 amp is going to give us 50 millivolts, which means we should get 5 volts out of one chip and 2.5 volts out of the other chip. So there I've set 1 amp. And you can see here we've got 2.5028, so we're within the 0.1% on one of them, and we've got 4.981. Now I don't know if it's the meter. One of these meters has a bit of an error on it, so let me just check which one that is. Well, oh, actually the easiest way is to just switch the connections just for a second. So let's just plug this one in here, and we get 2.497, but on here we're getting 2.5. So yeah, this is the one that's actually reading a little bit low. So sorry about that. I'll switch it for another meter. Actually, I have another one back here. I've forgotten that I need to calibrate that one, and I haven't done it yet. So this is just my 4th Agilent meter here. But it should do, is accurate, I believe. 4.988, so it is showing it a lot closer. So we've got 2.5 and we've got 4.98 volts over here. So now if I take the current up even higher, what you'll notice is that because the times 100 is already saturated, because it's a 50 milliohm times 100 and we're already at an amp, therefore it's already at maximum voltage on its output, it's really not going to go up anymore. But you can see the one with the times 20 times 50 is still able to handle a lot more current. I'm just slowly cranking this up. All right, so that's 1.5 amps going up towards 2 amps. So we're at 1.9. There's 2 amps. And now you see this one is now sitting with 5 volts. So by selecting a different chip, even with the same current sense resistor, I'm able to get a different output range. Now, obviously, if I wanted to have a low current range and a high current range, I could switch in 2 different shunt resistors, or I could have a times 20 current sense resistor to take everything from. I could have a times 20 current sense amplifier for the high current ranges, and I could have a times 100 current sense amplifier for covering the lower part of a range to give me more dynamic input. So I would use 2 separate ADCs or something like that to read those. There's lots of other ways to do things like that, and you could probably, based on what I'm seeing here, put both of those chips to the same current sense resistor if you wanted to as well. Now, if you really were trying to get a sort of a microamp, milliamp range and then have a big powerful amps range, what you may want to do is have 2 separate current sense resistors and maybe use a FET or something to short one out once you get above a certain range, just to protect it from overheating. So then you would be able to put something like 100 milliohms or 200 milliohms on one of them, and then have the 50 milliohms for the other range, and you get them in series and just switch the lower one out just to protect it, and then the other one would be monitoring the current via 2 separate current sense amplifiers. Anyway, that's pretty good demonstration, I think, there of what these can do as far as the straightforward current sensing is concerned. So let's put a comparator or set the comparators up on them, and we'll give that a quick go. Okay, so what I've done here is pin 5 is the reset input, so I've actually currently tied that to 0, which means that the alert outputs are not working as a latch. They will go up and down as the current goes up and down and exceeds or drops back below the threshold voltages. Pin 6 is the alert output, and I put that to an LED here and a yellow one up here for the so we've got 2 different alert colors. And what I've then done is I've taken pin 3, which is the set point, and I've taken it to a potentiometer over here. These are both just connected across 5 volts. Because there is a 80 microamp current flowing through here, and these are fairly high values, their settings are a little bit non-linear. But what I did was I just put a meter onto the set point pin so that I can read it. Now this is just rough. You'd probably have a D to A converter or something in real life doing this. So if I just put this back on here, we can see that I have currently got 2.5 volts set on there, and I've got 2.5 volts set on this one. So I've just basically split the rail. Yeah, 2.5 on both. So that will allow me now, if I adjust the current, if you can see here, right now both of these are, I don't know if I can get everything in shot there, I think I can. Everything is now set up, and what I can do is adjust the current so that as soon as one of these goes above 2.5 volts, and you can see this one, which is the top one, is obviously the high gain, that's the times 100. So when this goes above 2.5 volts, that's actually 1 amp. So you could call this a warning light if you like. So let me just crank that up and we'll watch the voltage. Alright, and I just probably spiked above it there when I did that. But if I come back down again, the light's going to go off. Now let me see if I can tweak the resolution of that a little bit so that I creep up on it a little bit more carefully. 2.3, 2.2, 2.3, 2.4, and it's still not on. And 2.5, and I don't know if you can see that. I can't tell on the meter, but let me just aim the LED more towards. Alright, so I think you can see that LED now with everything on, I hope. So the yellow LED is now on, and if I come back down a little bit, you'll see that it's off. So that's 2.44, 2.5 volts, and now it's on. Alright, now if I keep going up, of course, this second one with the times 50 gain is still sitting at 1.25 volts instead of 2.5. Now obviously the first one is capable of going up to 5 amps, so what we've indicated here is we've effectively hit half range just using that comparator. So if I keep now going up in voltage, alright, the first one is now getting close to its saturation of 5 volts. When that one hits its saturation, this other one should be basically going to 2.5 right there, and you can see the red LED has now come off and on, off and on. So as I go above and below 2.5 volts on this second amp now, it's also now tripping its alert. But now because I've got the reset lines tied to ground, they are not latching it, so they're staying up. Now if I go all the way back down again, I can make this first one go off once I get down there. There. Right, now if I take this latch input, which I've got here, and I take it to plus volts instead, now when I go over 2.5, which is going to be very close now for the first one, there. Now even if I go back down to 0, that alert is staying in place, so I know that that threshold has been exceeded. Now I can go all the way up now for the other one, and the same thing will apply to that. So I have to go quite a ways. 2.5 volts, now it's set, and let's come back down. We're back down to 2.2, 2.0, 2.0, and it's stayed on. So these are now working in their latching condition. Now to reset it, all you got to do is take the pin low, and then take it back high again, and it's reset. Now the first one has not reset because it is still in its alert condition. Let me just bring this back on again. Excuse the noise. Alright, so I have to go below the first one's alert condition. So let's keep going down here. Right, so now we're down at 2.4 volts, 2.3 volts. So now I can reset that one there. You see now they're both off. And I can then go back in, crank the volts way back up again. First one's now set. Second one is now set. And then if I come back down, they're both now latched again. So you can see you can work these in 2 different modes quite happily. So that's quite a nice little chip. If you wanted to have something set up with a current limit, you could be using a little microcontroller or whatever else, and you don't have to worry about the microcontroller detecting the overcurrent condition. It can actually, that output you could use to drive a MOSFET gate load to turn it off or something like that if you wanted to, or you could trigger an interrupt into a microcontroller to tell it to shut the outputs off or take some other remedial action depending on whatever you wanted to do for your scenario. But the nice thing is that once you've set up your D to A converter to set that threshold, or a pot, the way I've done it here, then you can basically, it just will run autonomously, and even if your microcontroller wasn't paying attention for some reason, the alert would not go unnoticed. Anyway, that's pretty much all you can do with these things. I mean, aside from reading the specs and hooking them up with different current sense resistors and things like that, that's pretty much covered it. So if you were one of the people that are doing the Element 14 road tests, good luck to you, and I hope this has helped you see how easy these chips are to use and what they can do, and give you a bit of insight to them and maybe a few ideas of how you want to do your road test. If you're any other engineer wanting to look at using a pretty much single chip solution for current sensing feeding into an A to D converter, high side or low side, these will work on either side, then give these a consideration. But aside from that, that's pretty much it for this TI Tuesday. So thanks very much for watching, and we'll see you next week.